Hello everyone, and welcome to this Houdini HIVE workshop. My name is Erwin Heyms, and today I'm going to talk to you about user-friendly production tools for procedural pipelines. So, I'm a technical artist, and I've been working at Ubisoft for the past 8 years at this point. I've worked on Ghost Recon Wildlands, I've worked on Ghost Recon Breakpoint, on the procedural tools pipeline, and most recently, I've been working on the Riders Republic. And then next to that, I'm also a Houdini teacher and mentor, and I've been for the past 5 years. Around 2017, I started making this course while I was inside Ubisoft. And I eventually developed this into a 35-hour Houdini Core Masterclass, a video course that was shared with the entire company and pretty well received. And since then, I've done some basic lectures at, say, for example, at MIGS. I had a master class in 2018. And most recently, I've been working on a new public master class in my own spare time. And this is under my own venture, Houdini Academy. And this is called the Procedural Asset Production Masterclass. So a little bit about that quickly before I get started. So what I'm working on right now is this large multi-stage masterclass. It's going to be several modules, and it's going to take people from beginner level to professional skill level, or at least the skill level I personally believe I have. And then I want to release this over the course of this year and into next year, with the first module released right now for free on my YouTube channel. So I'll talk more about this later, but basically a lot of the things I'm going to show you, a lot of the images and content in my presentation are from my masterclass. So that's where you can find some more information on it. So as for the workshop content, what I'm going to talk about is an overview of tool pipeline solutions. So basically, how can we build up a procedural pipeline for our games? And what are some of the practices and the types of tools that we can build? Then after that, I'm going to talk about and show you how to make a cache-based pathing tool. Now, this is going to build further upon the last workshop that Simon did. And this one's going to involve creating a little tool that allows us to draw paths and then save the results out to a cache and then iterate upon that result. So it acts somewhat like this, where we have a basic drawing capability. We can click points, it will path along the terrain, and then we can save that out and it adds it to the world. Next to that, after this workshop, I'm going to have a breakdown of a Pystate object editor, and I'm going to break down how this thing is built. Some of the most important parts on how to construct it. It's a bit too complex to talk about in terms of Python code specifically, but this type of tool is more than just Python code. You need to build an entire system around it to make it work, and I'm going to highlight how this is constructed. And then hopefully you can take it from there yourself. Plus, like I mentioned, I want to give you a basic preview of the masterclass. So with that, let's begin. So the first thing I would like to talk about is tool pipeline solutions. So when I think about procedural tools, there are a couple of types of tools that I like to discuss. And these are basically archetypes. So the first one is the canned asset, basically a standalone plug and play tool. You can just drop it down somewhere and it will work. The next to that, we have processors. So these are larger tools. Usually they're too heavy or too memory or time consuming to cook. So they have to be run on a render machine. That isn't mandatory per se, but these types of tools I put in a different category. Then we have the editors. These are usually a combination of various tools that facilitate an interactive workflow. They're lightweight to work with, but can be very powerful because they can make use of the ability that processors offer, for example. And then I also want to quickly talk about utilities. basically the simple, robust sub-assets that in larger projects you tend to build to make things a bit easier on you, automate some simple tasks. So let's go over each of one of these topics and go a bit more in depth. So the first one, like I mentioned, is the canned assets. And the canned assets are basically these tools that you can just drop down into your scene. If you have the Unreal Engine, you can grab it from your content folder, drag it into your scene, and it will start building something. For example, this is an elevator builder, and the idea is that you can just drop it down and configure it, and it will just run. And these things can contain all kinds of information, such as, for example, you can feed it information that can be gameplay related. In this case, the doors of the elevator, as well as the elevator itself, get configured. So you can actually traverse it. And these types of tools are very simple. You have inputs on them, usually parameters, maybe curves. You can have some geometry or terrain, and you just drop them into the world. You link them up to whatever input you have, and it will run. And this is very easy. These types of tools are quick and easy to hand off to your artists. These are probably the first type of tool that you'll ever encounter if you have never used a procedural tool before. Now, as for integrating them in the pipeline, well, we can use the Houdini Engine. It's very simple. In Unreal, we just need to have the Houdini Engine installed. We drag and drop it in the world and it'll work. And from there, well, most of the time you remove the asset after you're done, and then you have whatever you generated, like mesh data or instances. So the next type of tool that I want to discuss is the processor. And the processor is a type of tool that is best run on a render farm because of its size or because of the volume or memory load of the data that it needs to process. So let's say you have, for example, a large open world and you need to cut all your data that you have and group it into tiles for optimization for streaming. Well, then a processor will be the tool for your job, right? Other types of tasks could be optimizing LOD on large volumes of information, large volumes of meshes, for example, or just processing textures, like layering textures and compositing them together. That's what would be a great task for running on a render farm machine. So these types of tools take data from somewhere on your server. This can be in the form of textures, but it can also be in the form of curve caches that you've drawn somehow by hand, and then you have to run that through a processor. And then at the end, of course, these tools will output the data and they will store it somewhere. So it could be stored on a folder or on your server, for example. And then once it's done, you have all your data at the ready. So these types of tools in general integrate very well in a pipeline because you can offload them to a render farm and they tend to have easy controls. Your artists don't tend to really know they exist. And they can be managed through site apps like HQ or task operators, for example, in Houdini. Now, these tasks can be cooked daily or on demand. So you can use HQ to also trigger cooks by hand. Well, this output data that the tools produce can then be loaded back using loaders. So you have the data now stored on a cache somewhere, and you can have a loader that can then load it into your tools, or it can load it into your game engine. Plus, if you have a processor and you're processing all this data anyway, you might as well output all kinds of metadata about your world. So if you have a large open world, for example, and you're processing texture maps for, say, slopes and such, well, why not also output the slope map somewhere so you can load that in easily from somewhere else. Now, the next type of tool I think is a very powerful tool, and that's the editor. And the editor generally combines the different types of tools together. So in this case, they usually contain a very user-friendly UI, and you use data caching in order to allow very fast iterative workflows. And that's actually the type of tool that we're going to build in today's workshop. In general, you can use curves, you can use brushes, or even Pystate, so Python written handles for your viewport in Houdini, to quickly manipulate your data on screen. And then once you apply your changes, that change gets saved back to a cache. So it's very iterative and designer focused. Like here on the right, I have a basic brush, and then my placement system for this this kitchen assembly uses that brush as a placement location, and it moves the kitchen from its current preferred location to this new zone, and that's very fast. So in general, these tools need to be lightweight. You need to make sure that when you build them, the data that you're processing isn't going to bog it down, especially if you're using Python viewer states, because, well, if you start drawing and it has to cook half a second or longer for every tick you make a change, then your tool isn't very interactive anymore. So making your tool lightweight is important, requires a lot of optimization. Now, in general, I think these tools work very well when you need to give them to artists, because the input tools themselves are often relatively simple to use and quick to iterate with. Well, I think artists prefer these types of tools over the ones that you just drop down and then you have to configure parameters. But it depends, of course, because it also depends on the visual feedback that you set up for the tool. If your tool doesn't give enough feedback about what it's doing, then the artist might not like it, right? So next, they can also be a bit limited depending on how you build them. Like, for example, Python viewer states cannot actually run in the Houdini engine because there's no API connection there. As far as I'm aware, you can't install them in the Houdini engine. So these types of tools would then be limited to the Houdini viewport. Now, you can still take the data that comes out of these types of operators and then run them through HQ using a processor. So the editor portion can be a very lightweight piece that runs up front of what you are basically trying to process. So if you're trying to process roads, then the editor portion would be the drawing utility. And then the processor will be what comes after that drawing utility that processes all the information into the final results. So the editors are the part that your artist sees, and the cooking part that comes after, they don't actually have to deal with. Now, lastly, we have the utility assets. And the utility assets are these types of tools that facilitate a particular thing that Houdini doesn't do quite right or can't do at all, right? So think of, for example, importing meshes from a game engine. Oftentimes, we need to have a custom solution for that. And that's when we need to write this plugin that does that for us. So that would usually be utility. We don't tend to hand these off to our artists in our team. In general, they don't even know they exist. But us as technical artists, we become very familiar and we tend to use them all over in our pipelines. Other types of utilities we can think of are the types that improve upon existing Houdini nodes. So ones that add or improve upon Houdini's functionality. Over here on the right, for example, I have an asset that facilitates some of the cutting behavior that you might get from a Boolean shatter node or an intersect stitch node. But instead here, I took some of the combined functionality of the intersect stitch and the polysplit to make a more robust version of a cutting tool, where you can just take any kind of surface or a line and then subdivide a piece of geometry with it. And if you do this properly, and you make these tools robust, then you can use them all over your pipeline, and you can share them with people. And that's probably the most powerful part of utility assets, is the ability to just make your life so much easier. Stop having to worry about creating workarounds, for example. Now, if we think about utility assets, then there's quite a lot of them actually in the Labs toolset. It actually provides features that Houdini doesn't do by default, like extracting a curve from an edge group, for example. Simple stuff, but it doesn't come by default with Houdini. Now, as for integrating these into your pipeline, in general, it helps us integrate our tools better within game engines. Like I mentioned, we have the ability to import data or perhaps export some form of data from Houdini to the game engine. Well, that's where they are very powerful. And because we can share them amongst ourselves in our team, oftentimes the code of these utilities tends to be improved. Like someone sees a feature that needs to be improved, well, they improve upon it, or they make a version 2. And this allows us to speed up our tool development, as we're basically improving our tool set besides Houdini's toolset over time. And it will make these robust and powerful utilities that we use everywhere. All right, so in this next part, I would like to talk about how we can take these different assets that we just discussed and how we can turn them into a pipeline, how we can make them work together, and what role metadata plays in this as well. So the way how we build up our pipeline actually greatly affects how the final development structure of our team is going to work. If we set out to create a project with a very heavy processor-based pipeline, then we might need to set up a scheduler and run this during the night so that people in the morning have the latest data baked out and ready to work with. Whereas on the other hand, if it's a very canned asset, like drag and drop type asset, a heavy pipeline, then we need to teach these people how to use these tools. Depending on the way how you plan to use the tools and how they interact with one another, your pipeline is going to vary greatly. So I just want to discuss a couple of methods on how we can make these pipelines work. So the first type would be if we try to run tools in tandem or as batch jobs. And these heavily rely on having a wrapper asset or a larger tool that has subtools inside. And I'll quickly go over what this actually means in a minute. Then we also have the sequences, which would be if we run processors in, say, HQ. And then we also have these intermediate loaders. And in this case, we have a side asset that gets data from another asset. We process that information either automatically or customized by hand, and then we send it back to the main asset, kind of like slotting data back into the main asset. But regardless of which one you're using, they all heavily benefit from metadata. So information that the tools generate and then share with one another. And this allows us to make our pipelines much more responsive. And it gives us much more options about how we build our tools, because we have all this information about our game or our game world available from all the different tools that we use to build it. So the first type of method I want to discuss here is when we run tools in tandem. And when we run tools in tandem, it basically means that we are nesting them inside one another. So here on the right, you can see I have this elevator and a staircase over here that are being generated inside of this atrium environment. And the tools themselves, the elevator and the staircase, are both subtools. They are both standalone canned assets, but they also have this functionality that they can be hooked into a bigger asset as well. And this tool, it has the ability to slot them in there. So we have these slots here on the right that ask for these particular assets, and then they get configured, and then they just run. And by the end, at the end of this loop, we have a fully functional elevator and staircase, no matter what the shape of this atrium, because the atrium configures the tools. However, when we do build this type of tool, we need to make sure that the subtools are lightweight enough to run in this kind of configuration, or they might heavily bog down the final result. So a couple of pros versus cons in this type of configuration is that nested tools can be very heavy. They need to be light, and if they're not, then they will bog down your cooking. So you might need to set them up on a processor instead. On the other hand, if you run them in editors, which is where I think personally they work very well, then you can rely on cached data to make your tools faster. An example here could be that the elevators get generated and then the result of them gets saved to a cache. And then this cache is what's being loaded by the bigger tool. Yes, you need to regenerate the elevators if you change the shape of your building, but at the end of it, you don't have to worry about what they've cooked. They just ran and they're done. So the next type, or the next method I want to discuss is batch jobs. And when we run tools as batch jobs, we're basically running them using render operators or topnets, so procedural dependency graphs. And this allows us to very quickly generate a large variety or a large range of data from one asset. So one example would be if we use a compositing utility, for example, which takes different layers of terrain and all kinds of tiles, and then processes each of those over and over and over again until we get all of our tiles completely rendered. But next to this, we can also think of it as, say, a batch operation for a subtool. So in this case, here on the right, I have this tile builder, and I have all these variations of tiles. And they're all being generated from the same base shape. So this could be a mesh we load in externally and then run through this tool to cut it into the different tiles, or we can generate a mesh procedurally and do the same. And this is a very good suggestion for if you want to create a batch job, because the benefits of running a batch job is that you don't need to have dozens of assets in your scene to do the same thing. You just need one that gets constantly reconfigured and recooked and outputs the data after each cook. For example, here on the bottom right, I have 20 different pillars, and they're all basically the same pillar but with a different cutout. So if we run this as a batch job, we have one asset, and then we run that through a wedge node with render operators, for example, and by the end of it, we have all these pillars. We don't actually need to instantiate 20 different assets. On the other hand, configuring them takes a bit more effort, as opposed to installing 20 times your asset and configuring each one by hand. You would have to set up a CSV file or maybe a series of nodes that you plug into a merge node, and then you run the iteration using the data on those nodes. But of course, this way you don't have to worry about configuring everything by hand either. And if we were to run this using a task operator network, we can also distribute this over a render farm, and that makes it even faster as well. Speaking of task operators and HQ, over here on the right, we can run our tools as sequences. And when we run tools as sequences, it basically means we have a manager somehow, or a scheduler that triggers our cooks, that manages our tasks. So we can set up different tasks and schedule them together. So one series of tasks that completed, and then the next one and the next one. And eventually we output that data. So the pros and cons of this would be, it's easy to load data that's already pre-generated into a game engine, but it is susceptible to corruption. So if a cook on your render farm fails, it might have a domino effect down the line, and you might need to re-render the entire batch. And that can be especially frustrating if it takes an entire night to do so. On the other hand, you might also need a dedicated data manager, because the more tools you have and the more data you need to manage, you'll need someone who knows intricately how this sequencer is set up. But overall, the benefit is, of course, that if everything works properly, you don't have to worry about anything. Like, your render farm will just take care of everything, and the sequence you've set up will sort it all out for you. So the next type of tool would be if we create loaders. And loading, or side loading, would be when you take information from a tool, split it out, such as in this case over here on the right, I have this bigger building and I have this shape for an atrium. And I export this shape out to an external file and then load that into a separate tool. I can then use that separate tool to construct a custom atrium space and then save that back out into a file and read it back into the master tool. And as long as that configuration hasn't changed, it will fit in there and just connect up to everything. So this is a way to inject custom work inside of a much larger tool. Now the benefit, of course, for this is that loading it is much faster and it allows for more manual work. You can also debug the results of your subtools this way, because you don't rely on the main process, say the larger tool, to cook out all the data. So you have a much more responsive and more predictable set of data. However, of course, the results are static. So if your building is going to be changed in this case, then the atrium might not fit. And you'll have to restart all over again with making your own custom space, right? So you probably do this at the end of the process when you've already designed the shape of your structure and then want to inject this very customized space into that larger building. All right, so at this point, we've basically come to the part where we are going to start building our cache-based pathing tool. And this is an editor, just like I described earlier. And it's basically going to allow us to draw paths inside of Simon's little graveyard. And we can do this using an input curve. We just move the points and then we can add segments. And we can keep adding them because every time we add a segment, it gets added to the cache and then the load node takes over and updates whatever we're working on. Plus, we also have the ability to remove segments. And this system is built up out of 3 main parts. First, we're going to build the grid and then the recursive pathfinder. And these are the 2 main systems that allow us to draw our paths, right? That's the main tool component. Then we're going to work on the save load system that allows us to save our information to a cache and then retrieve it again and edit it. And then finally, we're going to add the UI and visual feedback systems. So let's get started in Houdini. So if you're starting on my course and you haven't followed Simon's course, then you can get the file straight from the SideFX site, wherever we get the files for the course from. If you have followed Simon's course and you would like to continue with his file, then you can do that, though I suggest you start with mine. But basically what I've done is I've taken Simon's file and I've added a couple of changes. I haven't touched this tool or any of his other parts here. But I've basically just set up some obstacles for the pathfinder to avoid. And next to that, I've hooked up my own tool into his. So I've done that by grabbing some information from the graveyard asset and then object merging it out using these object merges, such as his terrain over here. And I'm grabbing this from the cleanup layer games engine node, which is located here inside of his tool. That's for the terrain. And then next to that, I've also grabbed some obstacles. Firstly, I've grabbed the boxes that I'm using for the tombs. And then I've also grabbed the copy the points for node inside of his network, which contains the fence. So this one actually copies the fence pieces. And I need this because I need to make my pathfinder avoid the fence and the tombs. Everything else in the scene is going to be based on the paths, but these particular elements are hand drawn and I want to be able to avoid those. So for the rest, my tool itself basically just generates paths based on the terrain, a little pathfinding grid that it generates inside of this square. We can modify this square by either plugging in a box and then drawing out our own custom pathfinding area. Or we can leave it out, and without that, it tries to pathfind in the entire map. Though this might be a bit heavy, so I'm going to keep it plugged in. Next to this, if we look over here on the left, I have a couple of merge nodes set up, these purple ones, and these are to give you visual feedback. I've merged in his terrain, as well as the visual output from the cache-based path editor. So if you look on the right one, this path visualizer, this is good for when you're working with the tool. It's very responsive. And then on the left, we have all the visual information, such as the trees, the tombs, and the gravestones, and that's all present there. Plus, over here on the right, we have an output from the pathing tool, and this one provides us with the path network itself. I've added a stash node in between as well. So this acts as a buffer between my tool and the input to Simon's graveyard tool. Okay, so at this point, I'm going to start talking over the existing video I have, and I'm going to speed it up and slow it down when I need to. So first let me walk you over how the tool works. If I lock my screen in place and then I can grab my drawing curve, I can start drawing new segments. This will create new paths between the waypoints. And I can move the waypoints around, as you can see. It's quite responsive. So there's also a couple of settings. The first one here is the snapping strength of my different waypoints, and they will snap to existing segments of the roads into cache. Then we have the magnetize to cache feature. And this acts like basically a magnet for the new roads to make them follow existing roads in our world. If I set this to maximum or 100%, then you'll notice that it will snap to the existing roads instead of pathing the last segment directly. So that means that the roads will follow along until this point, and then instead of pathing to this last segment here, because magnetize is set to 1, it's going to actually back over itself, because these are really cheap, and then it's going to follow the existing road, and then it will branch off here, because it can't go outside this yellow zone, and then path the last segment there. Because this is the cheapest path. If we lower the magnetize value, however, then you'll notice how the pathfinder now branches off and follows this direct curve. Plus you'll also notice that the curve does this little bend here, and that's because it can't go up the little cliffs that are in the way. If I show my grid, then you'll see that the pathfinder cannot go up these areas. So instead it goes around. And it does that because there are a couple of other settings in play as well. But first here, let me show you what happens if I change the grid. If I lower the amount of vertical segments of my grid, then it has even less options to go up this slope, and it really has to go around this area, even with a lower magnetized value. So this is a very easy way to limit the way how your pathfinder goes up a slope, and instead forces it to make more shallow or zigzag routes. Next to this, we can also change the avoidance behavior of the pathfinder. So this red area around the obstacles, it's an increased cost value, and it means that if we increase this range, then it'll become more costly near these objects. So the pathfinder can still go there, but it will just dive in and leave as soon as possible. And then the last thing here is the turning cost weight. And the turning cost overrides the cost of turning. So every single degree it has to turn, it will increase the cost by this amount. Whereas this value here increases the cost per grid segment near an obstacle. So if you add those two up, the pathfinder will try to avoid obstacles, and it will try to avoid making as many turns if these values are very high. Now, as for using the tool, it's very simple. All we have to do is draw a path. Then we can click this Add Segment button, and this will add it to the cache. And then at that point, we have this added to the cache, so we can now start adding new segments as well. Plus, if we switch it to removal mode, we can then place 2 points or more on our existing curves, and then it will path between those over the network, and then we can remove that segment. So you see how it just vanished? The new roads now are marked as removal because that's the only path between these points. Plus, there's also this yellow box, the optional bounding box input, and this changes the area in which our pathfinder can path. If we disconnect this, it will now use the entire terrain. So this is how the tool works. And now I would like to continue with the main part where we're going to build the tool. This will take a little bit longer, so like I said, I'm going to speed up the video when we get to easier segments, and I'll go in more in depth and slower when we get to more intricate segments. So let's disconnect all these parts and remove the tool, and now we're ready to go. Alright, so let's get started. Let's create a new subnet node here. I'm going to drop it down, and I'll call this one the HIVE cache-based path editor. Now I want to turn this into a tool, so let's copy this and create a new digital asset. I don't really care about the path location right now, but let's make sure it has the right name, and then let's click accept. And this will create a new digital asset. So for this, I need to add 4 input parameters, 1 for each of these different inputs. So let's go to the basic tab and set the maximum inputs to 4 and the minimum to 3. So that's one for the drawing curve, one for the terrain. We have the obstacles and then the bounding box. For the outputs, we need 2. So that's one for the visualizer and one for the path output itself. Let's go here and let's give them some names quickly. So we have the editing curve, the terrain is the second one, obstacles, grid area, bounding box, and then the last 2 are the out for the visualizer and the out for the paths. Now here I'm going to click apply and let's connect everything up. Plus here on the left I want to connect these up so that later on I can work with them. Right, so now let's dive in. Let me delete this node and place a couple of null nodes down. I'm going to set up the inputs for this tool, and I'll do this a bit quicker. So let's create a couple of null nodes and connect those up. I'm going to name these based on their inputs, so they're easier to recognize. And what I also like to do is add a bit of color to them, so they're easy to recognize from a distance as well. So I'll color the bounding box yellow, the terrain green, the obstacles red, and the input curve blue. Now let's grab the bounding box and the terrain, let's move them on the left, and then place the input curve on the right. And with all of these, I can now add them to a subnet. So these are going to be our main inputs. I'm going to name this subnet inputs as well. So at this point, here we have the bounding box and the grid, and I just want to determine the actual size of the grid that we want to make. So create a bound node, and now I have a basic bounding box representation for our terrain. I'm going to grab a switch, and what I want to do is if the left input is empty, I'm going to use the bounding box from our terrain instead. So let's give these some names. Now in the switch for its script, I'm just going to give it a basic n-prims expression. So this will be if n-prims is 0, then use input 1 and otherwise use input 0. So like I said, if the bounding box input is empty, it will use the terrain instead. Now let's create a null node, and this null node is going to be a data carrier that I can reference. So I'm just going to call this blue. And now we're going to create our grid. So for starters, let's create a grid node. I'm going to call this one grid points. And I need to match this one to the size of our bounding box object here. So I'm going to grab the grid points node and create a spare input. And I'm going to copy the path from the path grid size in there. So now I have a spare input link created. I can simply type a bounding box expression in the size and say bounding box -1 is d_x size. This will give it the same size in x, and then we just copy this and put it in the other channel and set z, so we match both the x and z size as well. So now, depending on the size of our path grid size node here, our grid will have the same size. Next, let's add a centroid expression on the center channels. So we have the x reference. Let's call this correctly, centroid. Then copy it over to the other channel and set that to z. So now it will match the position as well. And last, I also want to make sure that this grid sits on top of my terrain. So I'm going to grab the get bounds from terrain node here, add a new spare input, plug that in, and then I'm going to reference the bounding box of that using -2 and its dy max coordinate. So now our grid will be on top of our terrain. Now at the moment I have too little points actually. Let's grab these 2 channels. I'm going to grab the second size value, plug it into rows, and then the first plug it into columns. And this will now match the points based on the size of the grid. So this will give us a basic set of grid points. And I've also switched the grid over here to point mode. Next, let's create a fuse node, plug it in behind the grid points node, and we'll call this snap to grid. And for this one, let's switch it to grid mode and give it a size of 5 on its grid spacing. And this will cause our grid to be snapped to a sort of virtual grid. And the benefit of this is that no matter where our grid is located, the points will stay in the same place. So now if I move this value around, then you'll notice that no matter where the grid is located, the points will stay in the same locations. And this is useful because we're going to use this point grid to create our actual grid connections, and we don't want those grid connections to be in different locations if we have a different input. This will allow us to work with our cache easier, because we need to match the paths in the cache to the grid later on. So next, let's go ahead and snap them over to the actual terrain. So I'm going to create a ray node. I'll call this one ray to terrain. Let's plug this in. So we grab the terrain on the second input, and let's change the direction so it casts ray downward. So let's set the Y channel to -1, and now you can see how it snaps down. Plus, if I use the entire terrain, you will notice that we have these points on the outside that aren't snapping. So I want to filter those out. Let's go ahead and use a ray hit group from the ray node, and then use a blast node to remove those as well. So we're just going to remove all the points that are outside of the ray group. Okay, so with that, we now have our points ready. Next, I want to process the obstacles. And to do that, here we have our obstacles, and they're coming from our object merge outside. And I have a silhouette from them using a lab silhouette node. So I'm going to grab my ray node, copy this over to the right here, and then I'm going to grab the channel from my terrain and position it right here. Next, what I want to do is grab a labs match size node, and this one will allow me to position the obstacles above the terrain, just like I did with the grid before. So here we have the grid offset. Well, I'm going to grab this match size node, and I'm just going to use it to change the Y channel. But I do want to leave the X and Z channel alone because I don't want to offset those. Let's change the Y value to max, and now the obstacles will always be above the terrain. If we plug this into the ray node, then now the obstacles will actually sit on our terrain, and that means that we can now use them to obstruct our path points and remove some of them. So next, create a transform node and a poly extrude node to create a basic obstacle geometry. Let's lower this down, so let's say by 5 units below the terrain, and then let's add a poly extrude. We'll just call this poly extrude collision, and I'm going to transform these up in global space by 10 units. So we have 5 meters below and above the terrain as collision space. That should be more than enough. So now we have our collision objects. Let's go ahead and remove the points that are inside of them. And to do that, I'm going to use a attribute wrangle node to write a little script for that. So I'm going to plug this in. Let's grab the points on the left, and then the second input is going to be our collision object. And I'll call this one the get distance to obstacles and remove them. So for this, the first part we're going to write is actually to get the distance from each point to the obstacles. And this is pretty simple. So let's say the float value, float at distance, is the XYZ distance of input 1 to our current point position. So basically, input 1 is our collision object, and then the point position is the current point we're running over. And the XYZ distance will simply get the distance between those. So let's add an annotation to that. Let's say get distance to obstacles. And the next part is a little bit more involved. We need to write a little if expression to check if the distance is too short based on a float channel. Then we remove them. So let's say if the float distance value, if it is less than the channel reference of minimum range, then we remove the point. So let's add some brackets, and let's say remove point So we reference our own geometry and then the current point number. This means that whatever point is within our range will be removed. If we click the button here, we can add a new control. And if we increase that, you'll see how the points are being deleted near our obstacles. So I'm going to set this to 2, because 2 meters is about enough. Now you'll notice that we have a couple of points inside of our obstacles, and that's simply because just the distance between the point and the hull is still bigger than 2 meters. So instead I'm going to reference the ray node instead, which is a flat silhouette shape on the terrain, and that works a bit better. So here it's connected to the collision hull, and if we switch it to the ray node instead, the flat shapes here, it will deal with it better. So let's plug that in and you see how it removes the points properly. But I still need this collision hull, so we'll use that for this next part. So now that we have our points properly set up, let's go and connect them. To do this, what I'm going to do is go over to the example file, and I'm going to locate the find shortest path example file. And this find shortest path SOP is a SOP that I actually co-collaborated on when I was running my internship at SideFX in 2013. And I created a couple of example files for this node. And the one that we want is called the path analysis node. So let's launch this, and this will open up a new Houdini session. And this is the example file for the find shortest path node. And this will generate a grid and then path over it. Now, if you want to check out this file, go ahead. It has a lot of information about how to use the find shortest path node. But what I'm looking for right now is this node here inside the environment and grid area. And this is the create ground connections wrangle node. And this creates the grid between the different points. So I'm actually after this one. Let's go ahead and grab this and the clean node as well. And let's copy those into our new scene. So we have the points on the left, let's plug that into input 1. And then our obstacle object and plug it into input 2. And now we need to configure it. So let's set the range here to a search count of 20. This matches our grid size of 5 meters distance. Then the primary search radius is going to be 12. And as you can see, we are already making some connections here. And it's avoiding the obstacles as well because of our input. If I disconnect that, you see how it moves over them. So that's all working properly. And then I'm also going to change the upper and lower range to 1 meter as default. And this will create a nice set of connections, especially around the hills. Okay, so I also have the clean node behind it, and this one is just simply removing overlapping pairs, but leaving one connection intact. So what I want to do next is grab the distance value that we're getting from our distance and obstacle remove node, and I want to promote it to primitive connections. So let's grab an attribute promote node, call this promote dist, and then let's promote the distance value from points to primitives. And I'm going to set the method to mode. Now I would like to view this, so let's create a visualize node and plug that in. And if I go to the visualize setting, let's switch it to ramped attribute. And I'm going to change this to the distance value on the primitives. Alright, so as you can see, we now can visualize our distance attribute. And I like to do this because it makes it easier to work with them. But let's continue on and let's create a measure node because I would like to grab the distance for each connection in my grid. So let's set this to perimeter mode. If we look in the attributes in the geometry spreadsheet, we now have the distance value and the parameters value exposed. And now we can calculate the weights for our grid. So I'm going to create an attribute wrangle here and call this one prim weight. I'm going to switch this over to primitive mode. And as for the code, we're basically going to set up the basic weights. So the weight is based on the distance to the obstacles. So I'm going to call this the weight value. It's a float. And then I'm going to use a fit function. So let's grab the distance as the initial value. And then I'm going to fit it between 0 and a fall off range. That's our maximum for the initial state of the fit function. And then I'm going to remap it to two different channel values. So the first one is the maximum weight. So if it's nearby an obstacle, the distance is 0, it's going to be a maximum weight, and otherwise it's going to be a minimum weight. Let's just, it's basically a basic fit function. And let's create the attributes here on the right. So now we can set some of the values. The fall off is going to be 10 meters by default. Then we have the maximum weight of 25 and the minimum weight of 1. So this, we should have a weight visible if I grab the visualize node. So let's set this up as the weight value. And now you can see that if I change the fall off value, for example, the red values near the obstacles get bigger. So this allows me to control the distance at which the cost of the grid is very expensive near objects. But I would also like to add a bit of extra cost for the travel distance as well. So let's type here ignore travel dist as a comment. And for this I'm going to create a float value called travel dist. And this is going to be 0 by default. Then I'm going to say if the travel dist value is enabled, then we're going to write it out. And we're going to use the perimeter for that. So if the ignore travel dist value is 0, then travel dist is going to be the perimeter value. Then we can take this and add it to our weights. So I'm just going to add this in here with a addition. Let's fix this because I need to make sure it's spelled properly. Okay, so now if I enable this, let me change the travel distance to a toggle, or yeah, let's change it to a toggle. So now I can make it add the travel distance to the grid, or I can make it ignore it altogether. This will means that diagonals and slopes in the grid might be slightly more expensive. It's important if you include it as a travel distance in your weights, because that means we can turn off the travel distance consideration on the find shortest path sub. And next what we need to do is add the turning cost. And this is to control the pathfinder's behavior a bit more, so it makes less sharp turns. Let's create an attribute wrangle. Let's set this up and call it the point turning cost. Plug that in. This one's a lot simpler. I basically just want to set up the turning cost, so it grabs the turning cost value from a controllable attribute. Let's expose that and set it to 1. Now I realized I plugged it in here as the second input. That is completely unnecessary. But anyway, you can see that I'm basically setting up the turning cost, and we also have the weights here. So now we have the basic path grid set up. Let's add this to a netbox. And I'm going to call this one the generate grid. All right, so let's save. And next what I want to do is add this to my interface. So the first thing I want to add is add a grid folder. And I'm going to do this a bit accelerated so it doesn't take too long. Let's grab the create ground connections control over here and grab the first 3 values. Let's plug those in. I'm going to rename these. So here at the bottom of the screen, I've demonstrated which attributes I'm renaming. This will allow us to change the grid setup. And here are the values that we should set on these settings. And then we have the connection complexity here, which I want to configure a bit more because this will allow us to control how the node will connect. Let's switch this over to use menu and switch it to replace. So we can grab an entry from the right from a drop-down menu. And I'm going to use menu item token as value as well. So it uses the value on the left. And the values I'm going to use here are as follows. It's going to be 5 and 4, 9 and then 8 for the label, and then 20 and 16. If I click apply and I look inside the grid from my interface, if I look over here on the right of my complexity, I can click on the different options and this will change the grid layout from 4 connections to 8 connections to 16 connections. And I can also increase this manually and change the values, but these are good default values to work with. Now I'm going to leave it at 16 for now, so this will work quite well. And now what I want you to do is quickly grab the value for the upper range and also copy it over here to the secondary lower range as well. So we change both the upper and lower range for grid generation. Next, let's go to our weights. Let's drag over these 4 values. I'm going to create a new folder here for this. Let's call this pathfinder. The first value I want to set is the ignore travel distance. Let's grab all the other ones as well, plug those in and rename those. So these are going to be the default values for it, as well as the names that I want to give them. So this is the obstacle avoidance range, that's the fall off. Now the default should already be mostly configured. The minimum weight is just going to be the minimum path weight, and then we have the maximum path weight as well. Let me speed this up a bit further. And then let's add the turning cost as well. So the turning cost, let's give it a minimum value of 0.001. And with all that, we have configured the grid. Now we have it over here. We can change the values on our grid. All very good. So next, let's go ahead and create a simple parallel pathfinder example. For this, I'm going to create a find shortest path node. And I'm going to plug the grid into the first input and then create a curve swap for the second input so I can do a little testing with it. Now, the find shortest path node by default uses the groups on your grid, but if you plug in a second input, it will use that instead. And we can now access the point numbers on that input to determine where the start and end points are. And it's going to try to find the closest point of that on the grid. So now if I click on the grid using my curve with 2 waypoints, you can see how it now paths over the grid. And as long as there's a connection to be made, it will output a line. So that's working quite well. But we cannot run this in a recursive loop just yet. We would have to wrap it inside of a for each node, or we have to configure our pathfinder to have more start and end points. But before we do that, let's first set up our weights. So we have those coming in from our grid already. Let's go to the primitive cost attribute. And let's add the weight attribute in here. So as you can see, some of our paths just jumped. They're staying away from our obstacles. That's coming, of course, from the primitive weights node. And then next, I want to turn on consider turning cost. And if you enable these 2 options and add in the turning cost attribute, then you can see that some of our paths just jumped a bit more, and that's because they're trying to avoid making too sharp a turn. And then last, I also want to omit the distance from the cost because we already added this value to our actual grid weight. And this comes, of course, from the measure distance node and the primitive weights node, which includes this value as the travel distance. So we don't actually have to use it here. And by including it in our main weights, it will work a little bit better. We don't need it here because it will simply double up the attributes that we're already using. So next, what I want to do is add a couple of extra connections. And to do this, we could, like I said, add more start and end points to match our input curve. And then we can switch it to a different type of method for pathing. So let's say from each start to a corresponding end. And this will basically group them. So 0 goes to 1 and 2 goes to 3. But if we want to set it, of course, to go consecutively, then we have to set it to 0 to 1, 1 to 2, and 2 to 3. If we don't fill in every single value, it will error out, of course. But this isn't very scalable. So to fix this, let's create a for each loop that's set to primitive mode. And if we drop the find shortest path node in this, we can make it loop. Now what we want to actually loop over is our input curves here. For every segment of our input curve, we're going to run one pathfinding operation. And for that, of course, I need a second input. So let's create a new input block here. I'm going to plug the grid into this second input block, the curve into the main for each input. And then I'm going to switch the second input block to fetch inputs, not to metadata, but fetch input mode. If I plug it in like so, this is going to start pathfinding, but we do need to make sure that our input curve is carved up properly. So let's create a convert line node, and this will carve our input polyline into different segments. So now each segment is going to path between its own 2 points. And if we then feed this into the pathfinder, you can see that it now paths properly. Now this isn't a recursive pathfinder just yet. This is just a parallel pathfinder. And for that we need to do a couple of other things. So at this point, we have a functioning pathfinder, but it's not quite the pathfinder that we're trying to create here. If we want to work properly for our recursive loop, we need to use a for loop with feedback instead. And this will create a repeating loop. This is a for each loop, that's a parallel loop. And this one's a repeating for loop with feedback. So what I'm going to try to do is loop our inputs, our input curves. And then for every single loop, it's going to loop it over into the next iteration. So we're going to add to our existing result every loop. So to do that, let's go ahead and grab the curve from the top. Let's bring it down here. Okay, so let's add a point here using the Alt key to create a permanent dot. And I'm going to prepare my inputs right here. So I'm going to create a net box for that. And I'm going to call this one snap to grid. And this will prepare our inputs so we can feed them to the pathfinder nice and clean. Let's go ahead and create a convert line node here. And let's plug that in. And I'm going to call this one convert line to segments. This will give me a clean segment for every curve I draw. So if I add a couple more points, like so, then here you can see we have one primitive for each segment. So now we have 4 segments. Next, what I want to do is snap this to the grid. Let's grab the line from our grid down. Let's create a couple of extra dots here. And then what I want to do is flatten them so I can snap them properly to one another. So if I look at this, what I want to do is snap them down and these up so they match the grid. Let's grab an attribute wrangle node. And I'm just going to quickly write out a simple flatten script. Let's grab the height from our point position first. And then next I just want to flatten the point position in y to 0. So this node will simply grab the height, store it as a height value, and then we're going to do the same thing for our grid. And next, let's grab a fuse node. I'm going to call this one snap to grid. So under this node, we're going to change it up. So instead of fusing our points, turn that off. And I'm going to set the snapping distance. I'm going to turn that off too. So it will snap to whatever is closest. And then I'm going to say closest target point. Because they're already flat on top of each other, this will basically just snap our inputs to the grid. Then what I also want to do is go down here and add a copy for the height. So this will copy the height to our input curve as well. So now that our snapping is done, let's take one of these wrangle nodes and restore the height again. And I'm just going to take the height expression and flip it around and then remove the flattened part. So as you can see now, the height is being set and it should now match our terrain. So let me visualize that properly. There we go. So now it matches it. And it should be correct in a top-down view too. It only snaps it downwards. So now let's go ahead and create a loop. Over here we have our repeat network. Let's go ahead and create a new one. Like I said, we want the for loop with feedback. And we'll call this one the recursive pathfinder. So next what I want to do is determine how many segments we want to loop over. We want to basically grab how many segments we have and then run it over the iterations of the for loop with feedback. So let's grab this value, create a null as a data carrier, and I'm going to name this null the curve count. Now let's plug this in. So I'm going to grab the curve count variable and I'm just going to sample the number of curves. So an n prims expression will do. So now that we have the number of primitives, this loop will run 4 times, or basically how many inputs we have. And then next, I want to grab the grid and the segments as well and feed those to the loop. So to do that, let's create a new meta import node by clicking on this button. I'm going to call this input grid. We'll change this to input type. And then I'm going to grab my grid over here. So now we have the grid information. Then let's grab it again and drop it down below our segments. Okay. And then this will give it our segments, our grid, and then we have the main loop. And lastly, I'm going to create a meta import node. And this is actually going to be a meta import node, not an input node. And this will grab the iteration count. And we do need this because otherwise we won't know which segments of our grid to filter out. Let's create an attribute wrangle node for this. We're going to say isolate current segment. And what I want to do is grab our segments and then under primitive mode, let's type a little expression to call out the segment we actually want for this loop. So we're going to say the current primitive number, if it is not the same as the current iteration, and we can use that using the detail reference here, then we remove this primitive. So 0, primitive number, and then 1 to make sure it also deletes the points. Let's call this remove non-active segments. So now depending on which loop we're in, it's going to grab its corresponding segment. If I quickly plug this into the end and then I go to maximum iterations, you can see how it grabs 1 for each loop run. So with that, we can already plug in our pathfinder. Let's go ahead and copy our find shortest path node. Let's plug that in here. Let's plug the first input into the grid and the second input into our isolated segment. And this will already allow it to path, so that's good. And now what I want to do is add this to our output line. So I'm going to add a merge node. Let's call this merge cached paths and live paths. I want to add it as a second set to the merge node, so it gets added after. And now what it's going to do, every time it paths, it's going to add it to the data from the loop and then loop it back to the beginning. So every next iteration is going to grab the previous loops. So if I change the iterations, you can see that from the input, we're actually retrieving the paths from the previous iteration. So we do now have two paths in this loop. This is the third loop, and it's got the last two paths inside the input here. And that's useful because now we can use it to determine where our previous paths are. For that, I'm going to grab these flatten nodes here and just drop them inside our loop, because I want to make sure that both the previous connections and our current grid are always at the same level. What I want to do is create a group that I can then copy onto my grid, so I know which parts of the grid are already pathed over. And this will allow me to override the grid weights with the existing paths. And then I can make those values 0 based on the magnetization value. Now to do that, we do need to make sure that we actually have the correct information from our find shortest path node, because right now our grid is made up out of lots of little segments. And as you can see, the output from our pathfinder is just two very long primitives. So in order to fix this, all we need to do is add a carve node or a convert line node behind the find shortest path node. And doing this will carve them into tiny little bits that match our grid, because the pathfinder just generates the curves from the grid it runs over. So we can actually get those connections back this way. And now, as you can see, if I refresh the loop, we now have all of the connections matching our grid. So we can use that. Let's add a group node. Let's call this one override. I'm going to call this the override group right here. And then we're going to grab a group transfer. And I'm going to transfer this at 0.01 range. And I'm only going to transfer the override group. We need to make sure we use the primitive groups for that, of course. And now if I look under the group window, the group display, I'll just give me this right color. You can now make out this curve in our grid as a group. So we can use that. Let's call this one transfer override. And now I want to restore my height, so I'm just going to copy the height restore node from up here and plug it in. And now finally, now we have our groups, we can use them to update our weights. Let's create another wrangle node. And I'm going to call this one override weight. So we're going to set this to primitive mode. And then let's say if the override group is true, then we override the weight. And we're going to use a magnetize attribute for that. So let's set this to f weight is equal to the linear interpolation between the original weight, a value of 0, and then whatever the control is. So in this case, the magnetized value. So if the magnetized value is 0, it's going to use the original weight, and otherwise it's going to use a value of 0, right? So if I lower this, you can see how the weight value on our grid is actually changing. Now we can plug this in over here. Now we just need to make sure that you set the actual group up here under the override weights. So it only applies this, of course, to the transfer override group. I seem to have mistaken here in the video. So we need to do one last thing, and that is add a removal for any overlapping paths. So if we create new paths, we don't want it to double up on existing ones. So let's create a group node here. And if the output from our pathfinder overlaps an existing path that came from a previous iteration, then I'm going to remove that segment. So let's use the same trick as we did before with the override. Let's create a group transfer, set it to a very low value, and then we'll just set it to transfer the new group here, the overlap group. So now we have marked the section that's overlapping between our two different sets of curves, and now we can just blast away the overlapping section. Now let's go ahead and add one more group here, and this is going to determine that this is a live segment. So when we're pathing new paths, we can identify them with this tag. So now we have our recursive pathfinder setup created. Let's add one more clean node to the bottom, just to be sure. And let's make sure that it removes any segments that were still overlapping from our input. This will remove any doubled up lines in our system. And with that, we have our basic setup done. So at this point, what I'd like to do is add some visualizers, because we now have a functioning pathfinder, but outside of our tool, it's not quite ready yet, right? We can see it, but it's just a set of curves. So what I want to do is have a better visualization for this. Let's grab our network here and quickly clean it up. So we add it inside of a netbox. I'm going to call this the recursive pathfinder network. And then let's create a visualizer system. Now for this, I'm going to speed up the video a bit more because this is relatively straightforward stuff. I'm going to create a netbox down here, call this the visualizer. And for this, let's first create a polywire so we can visualize our curves a bit better. Now let's give this a color. The default color is going to be green. Now I'm going to boost the colors to 5 instead of 1, and this will make them brighter. Now I'm going to use a split node up here to split the live segments from the cached segments. And then I'm going to copy this network onto the left and make this section blue. So our live sections will be blue and our cached sections will be green. So in the visualizer we can see which parts are new and which parts are old. And these are all going to be set to primitive color mode. So this way, if we merge them together, we have both our old paths and our new paths as a visual. And I'll call this one the visual for the add state of the tool. So next, I also want to create a couple of other visualizers. What I want to do up here is go to our poly extrude collision node and drag that off so I can visualize my collision objects. And let's just clean this up quickly. Let's create a color node for that. So I want to color these red. I'm going to make sure I delete my existing color attributes and set it to primitive color. Let's also add a normal, so we have a better normal representation. This should fix the normal if we set it to biface area. And then I'm going to pack this geometry because this makes it a bit lighter to visualize. Also, I don't need all these primitive numbers in my screen if I actually decide to show my primitive numbers. And finally, I'm just going to group it so later on I can filter out the obstacles if I want to. Let's go up here and set it to obstacle group. So now we have our paths and we have our obstacles ready. Now next I would like to visualize my grid. So let's grab the grid from the prim grid node up here and drag this down. And I just want to color it and make sure that I can turn it on or off using a switch later on. Now up here we have the visualize node that was showing us the state of our weight attributes, but the visualize node overrides our viewport. It doesn't actually add a color to the primitives. So to make it compatible with everything else, let's add a color node instead. And I'm going to switch this to primitive mode, switch it to a ramp from attribute, and then we're going to use the weight attribute. Now next I need to set up the colors, so I'm going to set this to blue, and let's make it a little pale. Then let's add a red color, and the middle color I'll just make yellow. So it's just a simple heat map type color scheme. So now I need to set up the maximum value for this as well, and to do that I'm going to grab the input curve and let's get the weight and promote it to maximum, and then reference it by the color node. So I'm just going to use a spare input here to the attribute promote, and I'm going to reference the weight value. Let's promote it to a detail attribute, set it to maximum, and then I'm going to just type in here a detail expression to grab it. That will give us the maximum weight value for this node. So let's add the switch next so I can turn this on or off in my viewport. I'm going to call this show grid, and with that let's add it to a subnet, call it the visualize grid, and then I'm going to plug it down below. So now we can turn on and off the grid in our viewport as well. And the last thing I want to do is just grab our grid points here. Let's copy this. I'm going to call this grid edge and turn it into a mesh, and then I'm going to remove all these subdivisions so we only have the edge. Then I'm going to resample this edge, so I have a lot of points on my edges. Let's say every 20 meters should be good. And then I'm going to resample it by the polygon edge, so we have a clean subdivision across the entire edge. If we then grab the ray node, it will snap to the terrain, and then we can use a polywire to visualize it. And let's add a color node so we can make this bright yellow. And then let's plug that in down below as well. Let's call this a visual edge, and with that we have our visualizer for the basic pathfinding system pretty much complete. Now let's go ahead and test out the basic pathfinder system. If I use the connection points, I can path in our scene, and for here we have our bounding box. So I need to make sure this is actually connected properly. There we go. So with that, now I can determine the size of our grid and path in very specific parts of our scene. All right, so it's already working. As you can see, it's avoiding the tombs inside of the graveyard. Okay, so with that set up, let's go ahead and add the magnetize control to the interface as well. And with that, we should have our basic pathfinder setup complete. Let's go ahead and go to the magnetize value inside of our loop. And I want to promote this to the interface. So I'm just going to add a couple of separators here so we have it separated out. Let's click accept. So at this point, we have our pathfinder ready, and next what I want to do is add the save load system to this node, so we can start adding and removing our connections to our cache. Let's go here below our pathfinder, and let's add a ROP output driver. Let's create a ROP geometry output node. And this node is going to save out whatever we've pathed and save it to a cache. Let's call this one the save add node. And then let's go ahead and plug the pathfinder into this, because we need to create a little bit of data for our cache. And I'm going to save this to a cache path. Let's add that one to our type properties. So let's grab those. And I'm going to promote the output file path up here to the top of our editor. I'm going to call this cache path. And as for the default value, let's switch this to the current HIVE file. So let's use hip/go/pathcache.bgo. This will save it to the same location as our scene file. Let's go ahead and apply this. And now, if we click the Save to Disk button, and now it will have saved it out to my hard drive as a BGO file. So next what I want to do is load this file again. So let's grab a file node. And let's call this one load path cache. So I'm going to copy the path from the ROP output driver and paste it into the geometry file field of the file node. And we need to make sure this is in backticks so it evaluates properly. And you can see we're now loading our file. Now, in case our file is missing, I also want to turn off the missing frame because I don't actually like it when it generates an error. I don't want it to crash the editor. Let's turn that off. And then I'm going to call this blue because that's a color to me personally as a data source. So next what I want to do is make sure that when I save, I want it to reload the file node. And to do that, I first need to promote the file nodes button, the reload button, to the interface. So let's go ahead and do that here. And I'm going to call this one reload cache. So now we have this reload button on our interface. And whenever I click that button, it's going to force the file node to reload the data. So next what I want to do is add a little link using the post render script from the ROP geometry output node, and that will then trigger the file node to reload whenever we save out a file. Now to do that we need to set it to Python mode, and the Python script will trigger a button press on the reload button on our interface every time it saves out, right? So as for the script, we're going to use the who.pwd command for our current node. So the node that got the button press, this ROP output driver. Then we're going to navigate up the network one level to the main asset using the // command. And then I'm going to reference the reload button on our interface, which is a parameter. So if we then reference the reload button, this one, or if we grab the parameter menu, here it is, we can then activate the press button Python function, and this will cause Python to press that button. So let's highlight this. That's the code we're going to use. So now if I go ahead and change my paths, then let's highlight this node so we see the results. If I move this around, and then I go ahead and save the data, you'll notice how the file node updates. So let's do that again. Let's move it around. This is what's currently our result. That's what the cache sees. If I go ahead and save, now my cache has updated. So that's the basic loop. So let's go ahead and move this up to the top of our network. And let's give it its own little netbox. I'll call this one the cache loading netbox. And now what I would like to do is take this network and make sure that it's snapped to the existing grid. So if there's a height difference between the terrain as it is and our data cache, I want my data cache to update so it matches the same height. Our grid won't change going from left to right or, in X and Z, but it might change in height, and I want that to match. So let's go ahead and copy our flattened network here that we created earlier. And I'm just going to replace this fuse node because I only want it to transfer the height. I don't want it to snap to anything. Let's delete that and add an attribute transfer. And we're going to call this one transfer height. And I wanted to transfer the height attribute at a range of 0.01. So this will make sure that the value is set properly. Now if I test this out, and I'm going to quickly deform my terrain here, and you see that the existing path coming from our cache is also updated. So our point should always be matching the points of the grid this way. So before we continue, let's go ahead and add another convert line here. So just in case our network is properly carved up before we feed it to the pathfinder. And this is where the magic really comes in. If we feed this cached path back into our pathfinding loop, it will treat it as an existing set of curves, as if it was a previous iteration. And doing so means that our next paths are going to see our old cached paths as a potential input. So let me quickly remove the transform node here. And then let's have a little look. So now if I grab my controller, I can move it around, and you can see how the pathfinder actually snaps to the existing paths that are in the cache. And they're actually marked green as well, which is because of the visualizer we set up earlier. Now we still need to actually link up the save node here, so let's go ahead and create a new parameter on our interface. Let's grab the type properties window, and I'm going to add a new folder called editor here for this. This is going to have all the different controls for the save load cache system. Let's grab the save to disk button from the ROP output driver and drop it in here. And I'm going to call this one save segments. And let's call it save so we can differentiate it easier, because we'll have some other ones in here as well later for the removal and clear system. So now if I go to the top of the network, you can see that we now have a save segment button here. Now I don't like how these tabs are lined up, so let's quickly click on these and change them to simple tabs, for now at least. So they're all lined up. And we can make it a bit more fancy using drop-down folders, but we don't need that right now. But now if we go ahead and grab our curve, we can add new segments like this. And if we click the save button on our interface, we've now added new segments to our cache. So that's working. Okay, so now let's go ahead and create an extra output point for our paths. Right now we only have one for the visualizer. We need to add one more. So let's go in here and add a output node. And I'll call this one output visualizer. This is going to be output 0. And I'm just going to make sure the normals are correct too. So let's copy that one and plug it in between. And then up next to the load node, the file node, let's create a null node. I'm going to call this one output, and then drop a new output node below that. And I'll call this one output raw curves. And I'm going to make this one blue, so whatever comes out of the network is the set of data. So now we have two output dots. Let's plug this in, because this will allow us to send our paths to Simon's tool. If we update the stash node, basically update our little buffer, then now, if we view the results, you can see that now our paths are represented in the world. So at this moment, we have the ability to add new paths using our path editor. And if we grab our curve editor here, we can add new blue segments. And then if we save, they will turn green. However, let's say we also want the ability to remove our sections from our cache. So let's copy our save add node and let's rename it to save clear. I'm going to snip the connection here and add a null node in front of it, which means that whenever we click this button to save, it's going to just empty our file with nothing. Now if I grab this, I need to break the link to our interface, because this is a new ROP output driver. And then I can drag it over into the interface over here below our Save Segments button. Let's rename this to Clear All. And as for the name, let's also call this one Clear. And then we'll apply it. So if I now go to the top of my network, you'll see that we now have a Clear button, and that will allow us to remove segments from our grid, and then we can save new segments into it afterwards. So we can now add and remove our sections. However, the moment we need to have more than one mode, it's actually better to add a little toggle, because we don't want to accidentally press this Clear All button and wipe our entire data set by accident. So let's create a new entry here, ordered menu, and let's call this one Tool Mode. And then under its menu, I'm going to add 3 values. First one's going to be 0, and it's going to be called Add. Then we have 1 for Remove. And then we have 2 for Clear All. And then with that, let's go ahead and add a separator in between this and the buttons. And now I need to set up the buttons so they only show when their own mode is active. So let's go to the parameters, and under the Hide When tab, I'm just going to type a little expression there. So for the Save button, the Add button, we're going to set it to if not 2 mode 0. And then for the Clear All button, it's going to be if not 2 mode 2. So now you can see that we have one button on the Add mode and one on the Clear, but we still need to add one for the Remove mode. So let's go ahead and copy the ROP output driver again, and let's call this one Save Remove. And I'm just going to add these to a little netbox so we can keep it clean. I'll call this one the Save Data netbox. Pretty straightforward. And to create a removal system, what I want to do is grab the cache loading information up here. And I want to make sure that this gets snapped to our existing curves. But to do this, first I need to actually have some curves to work with. So let's go back to the top level and quickly add a couple of them to our cache, because I just cleared all of them, right? Let's drag this around and save it out. So now we should have some data to work with. Let's grab this, and what I want to do first is make sure that when I have any connections from my curve controller, I want them to snap to the existing grid. Because if they're not snapped, I don't want it to select anything, because I don't want to accidentally remove parts I don't intentionally select. Let's go ahead and create a fuse node here that we can use for a snapping feature. So just like before, I'm going to use the fuse node here to snap our input controller to the existing paths. Let's set the snap distance, so I'm going to promote this to the interface. And I'm going to call this the cursor snap strength. Let's add it to the Pathfinder tab. And the default value for this is going to be 5. And let's lock it between 0 and 10 for now. And we need to make sure that we set it to closest target points, otherwise it won't snap properly. Let's grab the output from our existing paths and branch it off into the second input. So now, whenever we have a curve, it will try to snap to the network if it's nearby. And next, what I want to do is create an attribute wrangle to verify if these points are actually on the network or not. So let's plug it in like so. So what this wrangle script is going to do is that if the point is not on an existing path, then we're going to mark it for removal. So we just need to write a little expression to check if this point is actually snapping or not. So let's say if the near point, or basically the point that's closest to our current point position, is within a 0.01 range, which it would be if it was snapped, then if it's not that, then we go and mark it as an unsnapped point. So we'll call this one unsnapped as a group. And then if we look at the groups over here and then mark them, you can see that this point here is not snapped. If I disable the snapping feature on the fuse node, then the other ones will also be marked unsnapped because they're slightly too far away from the existing curves to be valid. So next what I want to do is just remove every point that is not snapped. Make sure we delete all the unsnapped points. And let's call this remove unsnapped. So with that, we now know if our points are snapped or not. And then we can just use a find shortest path node to create a connection between them. If we plug this in like this, where we have our existing segments, and then we have our points as our starting points, we can now use the asterisk symbol to mark every single point in our inputs as a start and end point. And what this will do by default is try the path between these points. But if you set it to the default setting, then the find shortest path node will just try the path to itself, because each point is valid as a start and end point, therefore there's no distance between the closest point, right? So we have to switch it to use each start to each end. And this will make it path from every point to every other point. This becomes heavy if you have a lot of points to path between, but in this particular case it's fine because we don't have that many connections in our grid. It's a very simple network and we probably won't need many points to delete anyway. So next let's just grab a convert line node and turn this into a couple of separate segments. Then let's grab a clean node and make sure that we clean up any double segments as well. And now if we have this, this will allow us to delete the selected segments from our existing data cache. So let's go ahead and plug this in below, and we need to create a group node here and then transfer it over to our existing path network. So we'll call this one remove segment and then transfer it just like we did before at a very short distance. So now if the path that the find shortest path node generates overlaps with an existing path in our cache, it's going to be marked as remove, and then we can just blast it away with a blast node. So let's go ahead and do that. And we'll call this one remove segment. And the reason I'm using a blast node here and not an attribute wrangle or anything, well, it's for simplicity. But this now works, so we can plug it into our remove output driver. And we need to make sure we hook this up to our interface as well. So let's go ahead and delete this connection and then drag it over. And in some cases, you might notice that Houdini doesn't like that because you haven't refreshed the type properties menu, like here. So what you want to do is just close the type properties and try it again. So let's drag it over. And this will be the remove segment button. Plus, don't forget that you also want to make sure that you set up the hide when tab down here. So if tool mode is not -1, it should hide it. So let's click accept on this. And the last thing I want to do is just make sure we clean our data, because it's important when you have data going in a repeated loop that you make sure you don't add it with junk data or double it up. So let's add a group delete here and remove some of the groups that we've added. Managing your data in an editor like this especially when you have a complex one, becomes very important. So let's go ahead and just set this to remove all groups. So I'm going to color those red because I like to color whatever deletes things red. And now let's go outside of our network and have a look at the features. If I switch it to remove mode, I have the remove button available, but we're still seeing the wrong visualizer right now because we haven't set that one up yet. But if we click remove, it will work. So you see it removes a segment. So let's now update the visualizer. I'm going to speed this up again because this is relatively simple. I'm basically just going to copy the previous network and color it red. So instead of the live segments, I'm going to use the remove segment, and I'm going to plug that one into the data up here, where it comes from the removal network. And right now the colors are wrong, so let's go and change the blue color, which is our selected color, to red. Let's grab this null node, plug that in, call it visual remove. And what I want to do next is just add a switch node, so we can switch the visual depending on our tool state. Let's grab the parameter from the top level, plug that in. And then our first input is the add mode, second one is the remove mode, and then the last one is going to be our clear mode. So let's grab that one as well. And for that, I'm just going to grab the full network, so we can use the existing link here coming from our removal network. And I'm going to color the entire network red instead. So if we're in clear mode, everything is going to be removed, so red means we're going to delete everything, warning, right? So now we have the network all set up and our visualizers too. And this is of course important because this allows our tool to represent what we're doing, and that will allow our users to understand what's going on. So if we test this out quickly, we can see that if we move our points around and wherever we have it selected, in between those parts, it's going to mark it for deletion. Now, there's just two last things that I want to quickly clear up before we finish. The first thing is that I want to grab my input curves for the Pathfinder and snap them to the existing curves, just like we did before with the removal system. So I can grab the snap control curves to existing paths node here and then copy it over and drop it in over on this side. This should be set up properly. So you see how it can snap if we increase the snap distance. I'm just going to wire it up directly to the node up here for cleanliness sake. And then the last one is that we need to make sure we set up our show grid so it can be toggled on and off. Let's go ahead and plug that in here, turn it into a toggle. And I'll call this one show grid. Now by default, I'm going to set it to 0, so it's not visible when we load in the tool. So now we are pretty much ready. Let's go ahead and test it out. I can show the grid, so that works. If I plug in the bounding box, we only have it in this particular selection area. And now let's go ahead and draw a couple of extra paths. So in add mode, I can start clicking around. And this works. Okay, we can save them. Now let's try to remove some. Let's grab a section of this path and then remove that. And now the last thing would be to check the clear mode. So let's clear all our connections, and that works too. Okay, so at this point we have a functioning tool. Everything is working. Let's path across the map and let's save this out. And then update our cache, so we send it over to Simon's tool. So now we can view the final result. And here we go. Everything works. It's all in the world. So that's the workshop part for the cache-based path editor. I hope it was clear for you, and let's go on to the next section. So in this next section here, I just want to quickly go over another tool, and that's basically a Python viewer state object editor. And this tool has the ability to take a data set, such in this case a set of instances that have been placed into this room configuration, and to grab it and move it around using a Python viewer state. So as you can see, I can just grab objects and rotate them and reposition them, and then when I'm happy with it, I can save it all out and it gets changed inside the data cache. So this is actually a very user-friendly and intuitive way of changing data that's already been generated before. So let's have a quick look at Python viewer state editors, right? Now I'm not going to go over the entire Python code here. That would go a bit too much in depth, and we already ran a workshop. But this is basically more about how to set it up. So this editor uses Python's viewer states and custom handles driven by the mouse. And it's a very user-friendly and interactive tool. And it's used to control data sets, to modify an existing data set. So it's based on an existing SOP node. If you're going to make a Python viewer state tool, you generally want to base it on an existing node and then add functionality from there. So in this case, I'm actually using the add SOP to create points, and then to modify them using the code inside the interactive section of the editor asset. So here you can see how we use the abilities from the add SOP to quickly add points into my screen. And over on the right, whenever I click, I actually add a new entry with the coordinates of that point, as well as whatever object I'm currently trying to assign. Now this set of information is basically written out to this multiparm and then instantiated using the rest of the tool. So the multiparm is just the base data, the list of data that I assemble when I use the viewer state. But then this information is then taken by the tool and used somehow. So in this case, whenever I click, objects are loaded from my hard drive based on the address that I'm currently trying to get. And then it's instantiated from the multiparm. So we also create a multiparm when we try to edit objects. These actually get stored in a separate multiparm. So if we have objects in our scene that are in the cache, or even new objects, these all have an ID. And we can then record which object we were trying to modify when we click on it with, say, the move tool or the rotate tool. And this creates a new entry in the edit multiparm with that ID. Then if we grab the object, the changes get recorded inside the multiparm. In this case, I can move the object based on my cursor position, or I can rotate it if I switch to the rotate mode. And the way how this works is by storing at all times the current cursor position down here in the cursor entry. So I know where the cursor is, and it actually hits objects in the scene, and it records that position where the raycast hits. And next to that, I'm also bringing up to the interface if I'm pressing the left mouse button for clicks, if I'm holding the control key, or if I'm holding the shift key. And I can use this to modify the behavior of the visual elements of the tool. If I hold the control key, my cursor turns darker. And if I hold the shift key, I get this move grid. So I actually ignore the vertical movement altogether. So next we have the ability to use the scroll wheel to quickly switch between modes of the tool. So we have the move mode, the up and down move mode. We also have rotation. And we have the ability to add new objects from an FBX file, or to mark existing objects for deletion. So these different modes, normally you would have to go into your interface and click the button, but by binding it to the scroll wheel, we can quickly switch the tool to different states. So like I mentioned, every object in our scene has a particular ID, in this case the primitive number. And when I move the mouse over an object in my scene, I can read out its ID and store that information on the interface. And this is very useful because this gives us the ability to create visual feedback. The ID is applied to whatever object is currently in my scene and given a different color. So when I move my cursor around, I can see visually what is actually being selected. And this is also important to then read out information from Python, but I'll go over that in a minute. Now here is a little overview of how everything works combined. As you can see, I can grab and move objects. I can add new objects as well. And then when I'm happy, I can apply those changes. Now, every time I move an object, the changes get recorded to the multiparm. And then those changes get applied to the original cached point data. They override the particular point that the edit is made on. Then, when I'm happy, I can save out these changes back to the cache file, and this triggers a reload on the load node, on the file node, that loads this cache file up top, like I basically showed you in the workshop. So this feedback loop allows me to edit objects. So grab an object, move it, edit it, and then save it back out in a very rapid way. Likewise, if I don't like my changes, I can also simply click on the clear all button, and this will purge the multiparm list, and we're basically just back to an unedited, pure version of the cache. So it's actually really important that the Python viewer state and the parameters know which current ID to modify, because the node uses the multiparms to create new data. And if we start writing out to the wrong multiparms using a Python state, we can actually break the tool's workflow. So in order to make sure this doesn't happen, we need to make sure we always synchronize our Python viewer state and our parameters. In this case, I only really need to sync the ID that I'm currently selecting, that's currently under the cursor. So like I mentioned, when the Python viewer state reads an ID from the geometry underneath the cursor, we then take this ID and set it on the interface. Then we use this parameter to drive the visual feedback elements, so us as the user can see which object was last modified or selected. But then Python will also sync its own internal variables from the parameters on the interface. So this means that Python writes out to the interface and then reads it back in to update its own internal variables. And now Python is using those internal variables for the internal code. By making sure that we sync the Python viewer state to the parameters, we actually avoid Python from throwing a lot of errors. And errors will break your tool, they will break your workflow, so we want to avoid those. So creating a very secure system for this type of tool, because we're interfacing both between Python and our node network, is very important. Now the last thing I just want to explain is how we can keep our tool working fast when we are dealing with FBX files. Because loading FBX files, especially if you have a lot of them and a lot of variety of them, is going to get heavy. In this tool, I actually created a cache loader that has a standard FBX file loading loop, just for each loop that loads an FBX file for every single unique object. But then below that, I have this stash node installed. And the stash node caches all the objects that are being loaded from the file node to memory. And then the rest of the tool just loads the objects from there and copies them to the points in the scene, to the instances in the scene. I only have to update this stash node whenever the information coming from the stash node doesn't match the information coming from my objects in my scene. And if there is a difference, then I can make Python cause the stash node to recook. That's when it updates the files, and then the stash node has the new data. So this creates a more staggered way of loading your files, and it makes the entire memory system a lot faster. So you can actually have an interactive viewport interface without constantly updating your file nodes, which is really slow. So with that, we've pretty much come to the last part of this workshop. And before I continue, I quickly want to recap some of the things that we talked about. So the first thing that we did is talk about procedural pipelines and the types of tools and methods that we can use to build them up. And I've highlighted some as examples as well. Then we went over how to make a cache-based path editor using a save load system and a basic pathfinding setup. And then lastly, we broke down how to build a Python viewer state based editor to take objects in a cache, move them around, and then save the changes back to that cache. And I just wanted to highlight that because during the course of this workshop, we actually covered several parts of my Procedural Asset Production Masterclass. Both parts that we talked about, such as the pipeline, but also the drawing systems and the Python script-based viewer states. They're all part of my masterclass. And I just want to talk about that a little bit. My Procedural Asset Production Masterclass is a large, comprehensive, multi-stage course that will teach professional digital asset development for game development pipelines. And I'm focusing on the Unreal Engine and world building type tools. We will start with basic beginner level canned assets, such as the elevator and staircases that I've shown, but we'll also move later on into much more complex tools, and we'll build this large high-rise building. Now over here, we have the Masterclass Introduction module, and this is the first module of the course that aims to teach complete beginners to Houdini the basics of procedural modeling and texturing, and then the ability to bring this into Unreal using the Houdini Engine. And I'm announcing right here that with Houdini HIVE, this is being launched completely for free. And I'll give you the links in a minute. So first, what I want to do is show you the trailer to give you a better overview of what this introduction module is going to be about. So today I'm launching the first module of the masterclass, and this one contains two parts. The first one is called Houdini 101, and will cover the basics of Houdini. So this one's for complete beginners to the program, who know nothing about Houdini at all. And then the second part is called the Foundation module, which will give you a good, solid foundation for working further in Houdini. We'll teach you basic procedural modeling, as well as basic procedural texturing, and instancing, so we can bring this all into the Unreal Engine 4. And build this building you can see down here. So the upcoming modules of the masterclass will cover other procedural tools as well that will later hook together to form a much larger project. So over the course of the next year, I aim to release 5 more modules for this course, each one teaching you different aspects, and will cover things such as elevator builders and staircase builders in the next module. We'll also be working on a catwalk builder, a procedural tile builder and instancing for the outside of our structures. We'll be working on a freeform building editor toolset for creating complete high-rise buildings with floor plans, internal layouts, corridors, and rooms. And then we'll be working on procedural prop placement tools, which start with manual prop placement tools such as the editor that I've shown you earlier, but also a complete procedural preset-driven placement system that we can just drop down on a room and it will lay out complete hotel rooms and restaurants and any other type of layout that we've previously defined. Plus, during the course, we'll also be developing several powerful utility assets that you can use in any of your projects. And the entire course will come with the example files and the Unreal project files combined. During the course of the actual masterclass, we'll be covering several different topics, including how to use instancing in Houdini and integrate it into the Unreal Engine 4. We'll cover advanced pathfinding techniques using the Find Shortest Path SOP and its many powerful capabilities. We'll be going deep into Vex and Python, as well as Python viewer states, in the final parts of the course especially. We'll be covering procedural pipeline design as a whole. This entire course is all about integrating tools together and making powerful tool sets. So this is definitely one of the major parts of the course. Next to that, we'll be building advanced editors that are very interactive and easy to use for users. And finally, we'll be covering some batch processing as well, so we can automate some of the tasks like generating the tiles for our building. So if you want to get started on the course, you can find it right now on my channel on YouTube under Houdini Academy. And if you want to learn more about my masterclass, you can visit my site at www.ehoudiniacademy.com. Next to that, this masterclass is only possible because of the support from my Patreon backers. And over the last year, I've had several dozen people join me on Patreon, and they've helped me develop this course, buy the software I needed and the hardware I needed to record all the content. So thanks to my Patreon backers, I'm now actually able to release this first module for free for everyone. Now, if you choose to become a patron for my project, you will get basic updates every day on what I'm doing that day, as well as weekly progress updates as I develop the course. Also, long-term backers and higher tier backers will over time accumulate discount credits for upcoming modules, which will of course provide you a discount whenever a module is released. And finally, I also offer mentoring and student guidance on my Discord channel. So if you're interested, please check out my Patreon site, and you can also read the FAQ on what it all means and the different tiers that are available. Of course, if you just want to join the community of Houdini Academy and follow me on my Discord channel, feel free to join there, or you can check out my Twitter in order to get updates on the course whenever modules get released. So yeah, thank you everyone for following along with this workshop. I hope it was informative, and see you out there. Have a good one.